Okay. First of all, I want to thank organizers for the possibility to participate in this offline conference. So my talk is about some constraints on Lorentz Invariance violation in photon sector from his observations from Tibet-ASgamma experiment and LHAASO experiment. So outline of my talk. First, I make remind short introduction about Lorentz Invariance violation. The second part of my talk is some kind of theoretical part. I will briefly review some actual processes which are maybe crucial to make some constraints on Lorentz Invariance violation in QED. This process may divide to two parts, which is crucial in the superluminal scenario. Superluminal means where speed of photon is larger than speed of so-called speed of light, because it's also speed of photon. In superluminal scenario, I will talk about two processes, photon decay and photon splitting, and the second scenario is subluminal scenario, where are two different crucial processes, pair production on solid backgrounds and photon shower formation in the atmosphere. And the second part of my talk is more experimental, where in this year we have two results of detecting gamma rays in PeV or sub-PeV range from Tibet-ASgamma and LHAASO. I will compare with results and try to make some constraints on the scale of Lorentz Invariance violation, and after that I will make a short conclusion. First of all, very shortly motivation of Polaris Variance violation. Some approaches to quantum gravity predicts some departures of Lorentz invariance. There are plenty of these approaches. For example, Relativistic gravity. Unfortunately, you cannot make some prediction to the matter sector, for example, to photons from directly from these quantum gravity theories. So one have to consider some other approaches. So very simple approaches is to start from modified dispersion relations for every particle. It is just simple approach, but working in this scenario, one can miss some maybe important effects. And more complex approach is based on effective field theory. The most general type of this effective field theory is called standard model extension, SME. By Kosteletsky and Kolodai, and some its generalization to higher order operators. But in fact, in this SME, there are plenty of operators, plenty of coefficients, and calculations may be a bit more simpler if you work in some subset of this standard model extension, if you preserve, for example, CPT or spatial isotropy or something like this. Okay, in this work I talk about photons. LAV in photon sector is in the modified dispersion relation approach is defined by this dispersion relation. The first term is a standard special relativity term, and you can add some high power of momenta to these dispersion relations, which are suppressed by some quantum gravity scale. Usually, people consider two leading order cases, linear and quadratic. Where sign plus is the superluminal photons and sign minus is the subluminal photon. In this work, I restrict myself to quadratic case. Whereas several reasons of it, I think so the linear case is suppressed. Where current constraints are really super Planckian, and in quadratic case, you can it is simpler to calculate some cross sections in effective field theories, which I will discuss later about it. So in effective field theory approach, for this quadratic case, you can write with Lagrangian, where I call EQG2 as MLV. It's the same approach. You obtain with dispersion relation directly from this Lagrangian, and yeah, super Planckian. Okay, I mean that the constraints on this EQG1 are larger than Planck mass. Okay. In addition to photon, to LAV in photon sector, one should consider LAV in electron sector, but there is a nice fact from with consideration of LAV in electrons. If you consider synchrotron radiation in Crab nebula, one obtains with very strong bound on LAV in electron sector, 10 to 16 GeV. So if we want to constrain MLV for photons at the level 10 to 15 or less, we can neglect LAV in electron sector. So the most popular time of constraints on MLAV in photon sector is photon time of flight constraints. I'm not sure what these bounds are very recent, but the order of magnitude is 10 to 10 or 10 to 11 GeV, which is 5 orders of magnitude less than with 10 to 16 GeV. So now we consider some modified processes in quantum electrodynamics, which are crucial for propagation and detection of very high energy photons. One can also add the production, but now I skip it. So propagation, during this propagation, the high energy photon may produce electron-positron pair on background photons. And this process is responsible for suppression of such extragalactic photon flux in the case of special relativity, but in case of LAV, it is modified. There are two channels of photon decay, which appears only in LAV case. These channels are photon decay to E plus and minus pair, and photon splitting to free less energetic photons. Last two processes can suppress or exactly eliminate the flux of extraparticle photons at energies larger than a certain energy. And come to detection with photons in the atmosphere. The crucial process for detection is the pair production of very high energy photon in the atmosphere, precisely in the Coulomb field of nuclei, for example, nuclei of atmospheric nitrogen. This is called Bethe-Heitler process, and this process is also modified in case of LAV. The first process is extragalactic photon absorption on extragalactic background lights. So the multi-TeV photons which travels from extragalactic distance may be absorbed on extragalactic background light via with Braid-Wheeler process, gamma-gamma to E plus A minus. In standard relativity, this direction holds above a certain energy threshold, and the cross-section peaks near this threshold. So, for example, for 10 TeV photons with the wavelength for ground photons is about the order of magnitude of 1 micrometer. And the observed cutoff in spectra of some extragalactic sources are usually explained by this absorption on E by L. And in case of subluminal LAV, with the threshold is shifted to smaller wavelengths, and so the universe become more transparent. Suppression of these TV photons extragalactic will be weaker than in standard Lorentz Invariant case. So the current constraints in a subluminal scenario are really better than time of flight constraints, and these constraints are of the order of 10 to 12 GeV. Let's come to these some channels of photon decay, where simplest channel of this decay is gamma to E plus E minus in vacuum. This process discussed from Coleman Glash and in many papers after that. So it is kinematically forbidden in standard LI case and allowed only in case of superluminal LV. If photon energy is larger than a certain threshold condition comes from energy momentum conservation, and just above the threshold, this process is very fast. So the mean free path is of the order of magnitude is 100 meters. So as this process is very fast, so even a single photon with energy, if detected, so we can make that constraint on this energy scale. So if we have more energetic photons, the constraint will be better, and in order to make these constraints, we need the largest photon energy. Below the threshold, photon decay is forbidden, but another decay channel is called the photon splitting may be allowed. The main channel of the splitting process in CPT even theory is gamma to free gamma, and in quadratic model, which I described some slides ago, we made some direct calculations of the splitting process based on Euler-Heisenberg-Lagrangian, and the width of photon splitting is the following. So the important thing is not only the width, but also energy loss. And this is the profile for energy losses. You can see that the most probable case is when photon loses a half of its energy. So this splitting process is the effective process to eliminate some high energy photons from the gamma ray spectra. Inversing the formula from the previous slide, one can obtain the mean free path for this photon, for mean free path for photon connected with that splitting process, and from that formula one can obtain the estimated constraint on the mass scale MLV. So you can see that the dependence of the distance to the source is very weak, but you can see also the dependence on the photon energy, which is a little bit worse than the quadratic formula. Now we come to superluminal scenarios, to the interaction of these high energy photons in the atmosphere. The main channel of the first interaction in the atmosphere is pair production in Coulomb field of the nuclei, so-called Bethe-Heitler process. After the first interaction, the air shower develops, and can be detected with shower can be detected by some arrays of shower detectors. The first interaction is the most energetic, and we will show it in the next slide that it is suppressed in case of subliminal LAV. And subsequent interactions are less energetic. They may also be important, but we miss them in the leading order. So this is the cross-section for beta-Pfeifer process in standard LA case. And in case of subliminal LAV, where with the beta-Pfeifer cross-section are modified by this factor. So this cross-section decreases as fourth power of photon energy and also logarithmic factor. But first, the interaction of photons in the atmosphere is usually described by depth of this interaction. The depth of first interaction is proportional to inverse beta-Pfeifer cross-section and is about 57 gram to centimeter to -2. And this depth increases in case of Lorentz Invariance violation photons, and when delta X, which describes the subsequent development of the shower in the leading order, don't depend on this LAV, but only in the leading order. So the prediction to the photon flux with deeper showers may be not recognized by the experiment as a photon shower, and so they may be skipped from the detection. So the detected photon flux gets reduced to this factor P, which is described by this exponent. I want to generalize the two different process, photon splitting and shower formation. They are of really, okay, thank you, of a different nature, but they lead to the same prediction to the experiment. The flux will be suppressed by the factor P in both cases of photon splitting and in case of shower formation as well. And let's go back to the pair production on backgrounds. To the subliminal case, we have two different bounds on LIV. The first bound is goes from the detection of extragalactic photons from distant AGNs. For this process, pair production on EBL is important, and shower formation is negligible because the energies are very small, and the distance to the source are large. And another type of observation is the observation of 100 eV photons from Crab Nebula or another galactic sources. For these energies, shower formation is important, but the distance to the source is small, and pair production on backgrounds is negligible. These two types of constraint are independent. But if we came, what happens if we came to one in energy of 1 PeV for galactic sources? We have, in addition to infrared extragalactic background light, we have CMB, cosmic microwave background, and in this plot you can see the dependence of mean free path for a photon on its energy. you can see that for one PeV, the energy, the pair production on CMB is the most effective, and the mean free path for these photons is 10 kiloparsec. It's really galactic scales. So sub-PeV or sub-PeV photons from galactic sources, if you consider with sub-PeV gamma rays, you should take into account the process of pair production of CMB and process of sharp separation as well. So I have not much time, but now came to experimental part. The first experiment I discuss here is the Tibet-ASgamma experiment. It is such quite old experiment set up in the mountains of Tibet and China. And in April of this year, it published a paper in the PhysRef lab about detection of sub-PeV diffuse gamma rays from the galactic disk, and which is the result of Tibet collaboration. This is a part of this result from the outer galactic disk. The outer disk is the part of galactic disk which is from the our side of the galactic center, and Tibet-ASgamma claims that they found that diffuse gamma rays of these energies with data is significantly larger than predicted by theoretical models by Lipari and Vernetta, but theoretical models may depend on some factors, and a month after that, some people, including Koldovsky and Aronov-Simikos, for example, suggested some models of these diffuse gamma ray flux which are consistent with Tibet-ASgamma data. We use these data points from Tibet, the prediction from theoretical models, which is this is the maximal flux. That may in some models with flux goes here, but in order to make some very conservative constraints, we make the maximal. We use the maximal theoretical model, and here we show the prediction of photon splitting of superluminal LAV scenario. It's the yellow line, and the not yellow, blue dot line, and yellow line is the prediction of subluminal scenario in which we consider both processes of shower suppression and pair production on CMB. The shower suppression is the leading order process. Okay, thank you. And pair production of CMB gives a correction to this shower suppression bound. So we take the maximal distance to the sources from this outer galactic disk as 5 kiloparsec. The absorption coefficient due to pair production of CMB is 0.73. Okay, and here is the constraints from Tibet. The photon splitting constraint is the best on superluminal LAV scenario. The photon decay constraint is a little bit one order of magnitude exactly worse than the splitting constraint, and on subluminal LAV we can obtain with constraint 10 to 13 GeV. Okay, now we came to LHAASO. LHAASO is a new generation observatory in China on the similar places as the previous experiment. And a month after the Tibet paper, it was published the LHAASO paper in Nature. Jose Manuel said about it already, and I skip it. In this paper, LHAASO claimed 12 sources with energy larger than 100 TeV. We presented energy spectra for 3 sources. Red data points is the data points of LHAASO, and black solid line is log parabola feed, and dotted line is the power law feed. And also, LHAASO claimed that photon event with energy 1.4 PeV is detected from the area of Cygnus cocoon. In that LHAASO paper, the authors presented the gamma ray opacity for these 3 sources, and this figure I used for obtaining the absorption coefficient for these sources. So I skipped some last energy bins, which with significance less, not more, less than 2 sigma. And here you can see the energy for that significant energy bins, and with the absorption coefficient or attenuation factor due to pair production CMB is 0.9 or even weaker, even less. So this slide presents the graphs for 3 sources discovered by LHAASO. The solid line is power law feed. Data points are LHAASO data, and here blue dotted line is the prediction of splitting scenario, superluminal scenario, and yellow line is a prediction of shower suppression and reproduction on CMB. So let us summarize the LHAASO results. In superluminal case, it was also made in independent paper by Chen et al. By a bit different analysis. Our analysis is weak, but I think more conservative. I'm sorry, did not take into account some points, non-significant last points. And here you can see the results. And also the photon decay bound obtained from the energy event with maximal energy obtained in the paper of Chen is 10 to 15 GeV. Give the same order of magnitude as this splitting constraint. Okay, now came to my conclusions. First, the stronger constraints are from Tibet-ASgamma collaboration due to the first reason is the largest energy for energy bin, but it may dependent of the theoretical model on diffuse flux. LHAASO will take more data, so better constraints are expected from LHAASO. And if you want to go up at this MLV scale, you should take into account LAV in electrons. And if you want to search for this deep atmospheric, search for subliminal LAV, one, I think, should make some analysis for search for some deep atmospheric showers. Okay, thank you for your attention. I'm sorry for
You obtain these bounds for the n equal to case, right? The quadratic case.
For quadratic case.
The quadratic case. If you take n equal 1, the case of subluminal scenario is acceptable. For example, Ma uses this scenario to explain the arrival of very high energy photons. Which could be the constraints that one would obtain in this case from the air showers formation?
Okay, with air shower calculation is based on with the calculation for Bethe-Heitler cross-section, which was performed only in case of quadratic. If you want to make some, if you want to make some quantitative constraints, you should make the similar calculation for linear case, I think.
But you don't know if the constraints would be compatible. I mean, it would be or the order of Planck mass or higher than that.
I expect that the constraints will be higher than Planck mass, but I'm not sure. I did not make these calculations.
Thank you.
Questions?
Yeah, concerning your limits, you said that they are a factor 2 smaller than the ones from the work from Chen because you are more conservative. So could you be more specific exactly in which you are more conservative and for which reason? Because is this work from Chen published under the label of the LHAASO collaboration? Because if that's the case, I think they have the how to say, the understanding of their data to decide whether that data should be used for the constraint or not.
Sorry, well, what exactly?
You understand my point? So if the people from the experiment decide that this data can be used, why don't you use it?
Okay, the paper by Chen was not a LHAASO collaboration paper, but about the difference between our work and Chen's work. For example, here you see two last point, which statistical significance is less than 2 sigma. Here is really less than 1 sigma. So I skipped these last points, these two last points, and here last point for these sources, I skipped only the last point because these points are good. So in the analysis, I include 2 points for each sources, the pre-ultimate, pre-ultimate, and for this source, and here this source. But I think so the results are similar, and it depends on it depends on the analysis. I think Chen's result is also good, and you can use them.
Okay, no, just a comment. I mean, the points at the highest energies, which are the ones that have the lowest significance, are actually the most important for this kind of analysis because the effects go with the square of the energy. So in this sense, I do appreciate that you want to be conservative, but if the people that does the experiment is sure that the significance is whatever it is that they have claimed because they understand their systematic uncertainties, and this really adds power to the analysis, I'm not really sure that not using these points is the right approach. But that's just my comment.
Okay, maybe.
Thank you.
So let's take a speaker again. The next talk is going to be by Jahed Abedi. For echoes from the
Oh, okay.
Okay. So this is not. First of all, I want to thank organizers for this opportunity, and I should say I changed the title because we had the tentative evidence already. So this is the title is now gravitational wave echoes in the GW19521 binary black hole merger. So this paper is going to be submitted very soon. I'm doing this work with our PhD student Luis Philippe Longo and Nilesh Abedi. So first of all, I will give why we are looking for echoes, the motivations, and then I will review their progress and former progress and all works about this. And I present the new results, which is search for echoes in gravitational data for this event that I mentioned in the title. So let's give a theoretical review. Event horizons in general relativity are a global property of space-time. We don't expect to see anything dramatic near the horizon when an observer falls and across the horizon. However, if we include quantum mechanics, there can be modifications because we have information problem. So if we need to, people think that we may need to give up one of the 3 times tested theories, Einstein equivalence principle or unitarity or existing quantum field theory. If we give up the equivalence principle, we see that we should have a fireball near the horizon. We can have because of quantum tunneling into the pulse walls, we may have strong modifications from standard GR near the horizon. So if we include quantum mechanics, theory puts Planckian physics at the horizon. As I mentioned, solving black hole information paradox or having black hole false ball, or gravastar or other alternatives to the black hole. So, so what we expect to see in the LIGO data. So assume that this is a black hole. Assume that there is a fireball. This fireball can play as a reflecting barrier to gravitational waves, so it can reflect gravitational waves. We have an angular momentum barrier far from the horizon, which is completely classic. So if these two barriers exist, this barrier already exists. If this barrier also exists, it makes a cavity for gravitational waves, and these waves can leak out in each process of reflection from the angular momentum barrier and make first echo, second echo, and third echo, and all the repeating echoes, as you see in this plot that we have first, second, and third. And they have a time delay, which is given by time for a light ray or gravitational wave that go from angular momentum barrier reaches to the Planckian proper distance from the horizon and reflected back to the same point. For example, for 300 solar mass black hole, this time delay is around 1 second, so it's long time delay, but it is not infinite. If we look at these echoes in the frequency domain, because of this repeating pattern, we expect to see resonance harmonics in the frequency domain, as you see here. So here in our new method, we use a model which is given by Oshida et al. Based on the assumption that we expect, it is natural to expect that the horizon reflects the gravitational wave with Planckian Boltzmann factor, because we have this already with this factor in the Hawking radiation, so it's natural to have such a reflection. If we assume this reflection, we have repeating echoes, and if in a geometric series, we can calculate this overall waveform. M omega is the standard GR waveform, and this factor is deviation from standard GR. So quantum mechanics imply that we have minimum Planck wave, which is 10 to the power minus 35 meters. So for the waves that reach to the horizon, this minimum distance is not zero. So this time interval is not infinite, so it's a finite time. And as I said, it is for 300 solar mass black hole, it is around 1 second. So we might have echoes at 1 second from merger time for GW190521, which is the most massive binary black hole merger event that observed to date. We use two software, which is people in the gravitational wave community are using this. Both of them are open source software. PyCBC, which is based on MCMC algorithm and using match filtering. And the coherent wave burst software is which is called, in short called CWB, is a software based on finding coherent excess of energy in several detectors. And this is model independent software. So this software needs model. This software is model independent. So in our first paper, we found evidence for echoes in O1 data, GW150914 plus GW151012, and Boxing Day event. So first, people were skeptical, but later a paper came from LIGO, inside LIGO and outside LIGO collaboration, that using this software, they were finding the post-merger signals in the time delays that we were looking for echoes. Exactly. So this is this is the signal from GW 150914. This is for GW151012, which is this signal, which is the loudest one. And this is the Boxing Day event. They also reported this in the same time delay. We also did a PyCBC search for them, but the evidence were not big enough, and the signals were weak. So we think maybe we should use a better waveform, which is I mentioned, Boltzmann reflectivity waveform. And we use the former method in search for O2, and GW170729 has shown big evidence, but it's not big enough. So maybe we should use a better waveform, because we don't see significant echoes. But anyway, when the amplitude is bigger than 0.3 compared to the main event, it shows in both CWB and PyCBC as positive evidence. So what about GW170817? This is the BNS merger event. We look for echoes in this event because it may have collapsed to a black hole, because it is inside the range of around 3 solar mass final merger. So it may have collapsed to a black hole, and the collapse can make a gravitational wave, and this wave can, if it is a fireball black hole, we can see echoes from that. We looked for echoes in expected time delay after the merger, and used another method, which is frequency, looking at frequency harmonics inside 60 to 90 hertz. And we found that around 4 sigma, there is a peak of a signal of resonances in the expected time, as you see in this signal here at 1 second. So we received a confirmation with another paper, which is based on electromagnetic observation. They found that this merger should have collapsed to black hole at 1 second, which is the same time delay that we found the signal of echo. For other people, they also look for echoes, and almost half of them they didn't find positive signals for echoes, and other half they were finding either mixed results or negative positive results. We report that in this our paper, our review here. There is a paper by LIGO collaboration that they were using, looking for almost most of the significant events, and they were using a prior range that was not, I mean, the priors that we were using, and it's not as physical. And as you see, the time delays between echo are fixed for all the events. It's not, I mean, reasonable, because the different events have different mass. But anyway, they were not finding significant echoes, and the short answer why they are finding is that there is no loud echo in LIGO and Virgo data. Let me skip this. So we did look for echoes in GW19 of 521, which is the most massive and energetic black hole merger observed yet. This is this big guy. So the model that we use is Oshita et al., which is this one. As I mentioned, if we have M omega, we have this part. If we have this factor, we have this repeating echoes. So in our first stage, I use a ring down waveform, which is consisted with GR part, and plus echo, which is the Oshita et al. Inclusion of that waveform. And I use the PyCBC, and I was finding average wave factor of around 8 now in preference for echoes, substantial evidence. And you see that this has non-zero amplitude. I use IMR plus echo, IMR waveform, and it is finding the same result, average wave factor of 8. So the expected region for echoes is inside this. So regions, this region is the expected region based on GR for first echo. This is the second echo place that we expect to see echoes in based on only using IMR. No echo is based on mass and spin we expect to see here. And we found that when we cross correlate two detectors, we and plot the spectrogram, we see that this peak here, and for this peak for second echo. So there is a bit deviation from expectation, because these peaks are not exactly at the center. So maybe there is a this is a super Planckian echo. I don't know, but if we assume super Planckian, they fit better in the base our expectation. So I put assumption of super Planckian. I mean, the Planck length is different, so it varies inside this range. And I was finding a base factor of around 7 preference for echoes. So maybe it's not super Planckian, because the waveforms or prior range can affect the results. It is only, I'm talking about around plus minus 5% error. So if the waveform or prior range is in a way that you the mass of black hole is around 280, it is a Planckian. But if you are using a waveform and prior range priors that is giving you lower mass, there is a better preference for super Planckian. Our student Luis Philippe Longo is doing CWB search, which is model independent, and using this software is based on coherent excess of energy in the same location of sky. So this is the main event, and this second pulse is the first echo that we are finding, but this is independent software, which is CWB. It is so he's finding that. So if we plot the reconstructed waveform by CWB and the most likelihood waveform from the CBC, we see that they are consistent with each other. So they are consistent. So if we plot frequency and time plot, we see that. So here these curves are the most likelihood waveform. So here we have first echo, here we have second echo, and this is the main event. If I plot this waveform in the frequency and time. So if there is no echo, I mean this is only GR, we just have this. So we are finding that with CWB, and they are consistent. I mean both CWB and CBC are finding that. If we use our waveform, the CBC is finding with base factor of 8, first echo and second echo here. And this is the result of this density plot, this is the result of CWB, and they are matching together. This is both my cross correlation of two detectors and CWB, they are consistent. When we cross correlate, we also find the signature of second echo in the plot. Our student Luis also is doing skull location consistently with skull location, but this comparing main event and the second first echo, and the results doesn't show any preference for echo or no echo, so it doesn't give much information, and the base factor is around 0.3 and doesn't give any information. So it's consistent with itself. So to conclude, although no clear and widely accepted observational signs of echoes or deviations from vacuum GR have been observed in gravitational wave detectors to date, we might be close. GW190521, which is the most massive event observed to date, has a loud echo signal. Results of CBC and CWB pipeline match together. Thank you.
Just a simple question about your waveform. So you have the quasi-normal modes coming from GR and you multiply it by the Boltzmann factor. So what is the motivation? Is there another way to obtain the echo just having like from perturbation theory, from a theory of quantum gravity, since the motivation is coming from quantum gravity?
Yeah, the motivation comes from quantum gravity. I mean, if we have a modification from classical GR horizon, we would expect echoes. I mean, if there is no event horizon, we would expect echo. If there is a modification from classical GR horizon, if they are big, we expect to have echoes.
Okay, and when you said we are close, so we miss it because we have less events, and
maybe I mean we are finding that in the GW190521, which is the most massive, the more massive events always show more stronger signals. Maybe there is a dependence on initial conditions. I mean, mass ratios, I mean, it can affect the result. If it is low mass ratio, even maybe doesn't show, or high mass ratios, maybe they are showing. So we are not finding in all of them, not all of them showing significant echoes. This is the message of LIGO paper. But we may, as I said, we may are close, because maybe we see more of these GW190521, and then we conclude that.
Thank you. Just a last question. Can we have the same form or closer by just quasi-normal modes coming from modified theories of gravity?
What?
Because we know that in modified gravity, the modes are shifted or we have new modes. So
Okay.
can we have modes coming from modified gravity that can be closer to the form of equals that you present?
So if, if there is a, as I said, in modified gravity, if you have a horizon, GR, if you have a horizon, these echoes will not be generated, but you see the deviations because you are finding different modes, and you see the deviation here. So you should look at here, above here.
Okay.
We have a paper with our Max Planck collaborators that we are finding for this event, which is the loudest one, 3-3 mode at 100, which is an expected frequency of around 100 hertz. Okay. So my last paper is about that.
Okay. Okay. Thank you very much.
Thank you.
Yep. Thanks a lot to the organizers for giving me the opportunity to give the talk. As the title says, I'm going to speak about the teleparallel analog of Horndeski Gravity. In the first part, I'm going to introduce Horndeski theory of gravity, which is the most general scalar tensor theory leading to second-order field equations. And I'm going to talk about some constraints to this theory from the gravitational waves. In the second part, I'm going to introduce teleparallel theory, which is an equivalent theory to general relativity, just using another connection. So just the geometry is different. And in the third part, I'm going to connect these two, and I'm going to formulate the Horndeski gravity in the teleparallel geometry. And I'm going to show you some applications also. And the talk is based on these 4 papers that are done by me and some collaborators here as well. So yeah, let's start from the Galilean scalar field, which is a scalar field that respects the shift symmetry. The most general Lagrangian that this field has and gives second-order field equation is this one in the Minkowski space. So X is the kinetic term of the scalar field. You have second-order derivatives of it as well, and also some polynomials of second-order derivatives, but still it gives you second-order field equations. And of course, this has no gravity. So if we want to introduce gravity as well, we just covariantize, let's say, the theory, and from the flat metric, we go to an arbitrary metric, and from the partial derivative, we just go to the covariant derivative. And by doing this, we indeed get some higher order derivative terms in the equations. And in order to cancel them out, we have to introduce these 2 terms here. So the Ricci scalar and the Einstein tensor coupled to the second order derivative of the scalar field as well. So this is the covariant Galilean theory. And we can generalize this covariant Galilean theory. I mean, these CIs are just constants here. But if we promote these constants to arbitrary functions, so the scalar field and its kinetic term, then we have the generalized covariant Galilean theory, which is exactly the Horndeski gravity. And it's the most general scalar tensor theory with a single scalar field in 4 dimensions that leads to second-order field equations, both for the scalar field and for the metric. Of course, this is a huge theory, and subclasses of it is known scalar theory, scalar tensor theories like Brandstike one. So if you take the G2, G3, and G4 and G5 to have this form, you end up with Brandstike. If you write down f of r gravity as a scalar tensor theory, you can map this also to the Horndeski action. And of course, it contains infinite subclasses of other theories as well. However, this theory was constrained from the gravitational waves because, I mean, the speed of the gravitational waves is given from this formula in the theory. And if this has to be one from the observations, as we know. G4 has to be only a function of phi, so it doesn't depend on the kinetic term of the scalar field, and G5 has to be constant. So it's just, I mean, it doesn't depend neither on the scalar field nor in the on its kinetic term. And as we'll see, this does not happen in teleparallel theory. So yeah, all these theories, quartic, quintic, Galileans, Fab4, and like some couplings of this term, like with the Einstein term, are all excluded from the gravitational waves, even though indeed some others survive. But for example, these have some interesting phenomenology, like predicting inflationary solutions and also self-accelerating solutions. But they are excluded from gravitational waves. Let's go now to the teleparallel framework. So the most general action one can write down, connection one can write down is this one, where this gamma with the circle on top is the Levi-Civita connection. This K is the contortion, and L is the distortion tensors, which depend on so this T is the torsion tensor, which is the antisymmetric part of the connection. Q is the non-metricity tensor. And of course, another property of the connection is also the curvature. Here is a schematic representation of these properties of the connection. So if you parallel transport a vector along itself in a manifold where there is curvature only, we end up with a different. I mean, the vector is different here. So this is proportional to the curvature of the manifold. If you parallel transport a vector along another vector in a torsional spacetime where there's no curvature and no non-metricity, the parallelogram will not close, and this open space here is proportional to the torsion of the spacetime. While if you parallel transport a vector in a non-metricity, non-metrical, let's say, spacetime, it will change its length. Here is a schematic representations of these theories. So this is the most general one, which is the metric affine theories, containing both curvature, torsion, and non-metricity. While of course, if you select the curvature to be non-zero and all of them to be zero, you end up with Riemannian geometry. If the curvature and non-metricity are zero and torsion is not, you end up with a Weichenbach geometry. And if you select the torsion and the curvature to be zero, you have the symmetric teleparallel geometry. All of these are three different geometric frameworks, but totally equivalent in the terms of field equations to Einstein's general relativity. So yeah, the teleparallel equivalent of general relativity is again the theory which uses torsion instead of curvature. The connection of the theory is given from here, the Levi-Civita plus a contortion tensor. And the torsion of the spacetime is defined from the difference of the antisymmetric part of the connection. The relation of the Ricci scalar and the torsion scalar is just, I mean, the difference between the two is just a boundary term, which doesn't contribute, of course, in the action. And so we end up with, I mean, dynamically equivalent theories. So this is the action of the teleparallel connection. You just have the torsion tensor here. E is the dynamical field, which is the tetrad. And these are the equations of motion. This left-hand side here is the Einstein tensor written down in the teleparallel geometry. And the motion of a particle in this framework is given by, so the analog, let's say, of the geodesic equation is given by this equation, which is, as we see here, resembles more to the Lorentz equation, Lorentz force, because, I mean, gravity acts indeed as a force here and not as geometry. Okay, some notation information. The dynamical field in the theory is the tetrad, and the relation with the metric is given by this, and this is the inverse tetrad and the inverse metric relations. Of course, the tetrad satisfies some orthogonality relations, and the teleparallel connection is given by this formula. So this is not the Weichenbach connection. The Weichenbach connection would be when this spin connection would be zero. This is just a Lorentz connection. Yeah. So yeah, if they're equivalent theories, why should we bother? Because indeed this teleparallel framework has some advantages. So it could survive without the equivalence principle. I mean, GR is based on the equivalence principle, but the teleparallel equivalent of GR, since it's a gauge theory of translations, it could survive even without it. It is also argued that it complies better with Newtonian gravity and the weak field limit, because also Newtonian gravity could survive without the equivalence principle. As I said, in GR, gravity is geometry, while in DGR, it acts more like a force, which means actually that the energy momentum tensor in this theory is exactly the nether current of the translations, and also it resembles more to, of course, it differs from U1 or Young-Mills gauge theories, because it's built on the tangent bundle. Which is soldered and not internal like the other gauge symmetries, but it still keeps the properties of gauge theories. And now we move to trying to connect these two, so teleparallel geometry and Horndeski gravity, and we want to formulate the teleparallel analog of Horndeski, and we have to set up some conditions, some criteria for this new theory to fulfill. We want, of course, the field equations to be of second order in order to avoid ghost instabilities. We want the scalar invariants that take part in the action to be non-parity violating. And we want also to have contractions of the torsion tensor up to quadratic terms, because even though, for example, the HC scalar depends on second order field equations of the metric, the torsion tensor, the torsion scalar, depends on first order derivatives of the tetrad, which means that one could construct infinite contractions of the torsion tensor. But I mean, we thought it's going to be more physical, let's say, to keep up to quadratic contractions of the torsion tensor. How do we do it? We decompose the torsion tensor into its irreducible parts. This is the axial part, the vectorial part, and the tensorial part. And we contract the scalars, the respective scalars. But we do not include in the theory parity violating scalars, as I said, as it is, for example, this contraction or this scalar, which contains the Levi-Civita tensor. So again, starting from a Galilean Lagrangian in the Minkowski space, we covariantize it, but in the teleparallel framework. So from a trivial, let's say, tetrad, we go to an arbitrary tetrad, and from a partial derivative, we upgrade it, let's say, to a covariant derivative in this geometry, and we end up with again, of course, exactly the same theory written down in a different way. So here, instead of the Ricci scalar, we have the minus t plus the boundary term. And here we have the Einstein tensor written in this geometry, which is exactly the same as before. However, we have some more freedom here because of the fact that the torsion scalar depends only on first order derivatives of the metric. We can also construct, as we see here, contractions of the torsion tensor irreducible components with the first order derivatives of the metric, as well as quadratic contractions of the torsion tensor and the derivatives of the metric. Of course, not all of these scalars are independent with each other. So we have some linear dependence, for example, with G6 and J6 and J7 are related like this. J3 is equal to J4. This J2 is just quadratic of I2, and this J5 is quadratic of I3. So we end up with a function with only the independent, let's say, scalars of the new framework, let's say, and we have the old Horndeski Lagrangian plus this new function of teleparallel quantities. So just by changing the connection, being not symmetric and being anti-symmetric, so and setting curvature equal to 0 and having torsion in this framework, we have this new term here, which adds, of course, a lot of phenomenology to the theory. The propagation of the gravitational waves in this theory is given by this formula. And I remind you here that in the standard Horndeski gravity, of course, we can derive it from this formula as well. So if we set G tele to be 0, we end up with the Horndeski limit, let's say, the speed of gravitational waves in the Horndeski gravity. And we see here that there are some terms of G5 and G4 also that survive. So those theories that were excluded, let's say, were severely eliminated in the previous framework, like G4, X, so the dependence of the kinetic of the G4 to the kinetic term of the scalar field, and also of G5 to the scalar field itself, revive in this framework. And with them, of course, all of the models that explain inflation or late time acceleration, they also revive in this framework as well. And some more applications have been done in the last 2 years. We also found the GW polarizations. So these two first are related to the scalar modes. These two are the vector modes, and these two are the tensorial modes, the known from general relativity. And as you can see here, which you can find in this paper actually, we classified all the subclasses of this general theory, the teleparallel analog of Horndeski. We found all the polarizations that they predict. Both we did an SVT scalar vector tensor decomposition, and we found its propagating degrees of freedom and the polarization modes. Also, the PPN analysis have been done. So, of course, if one wants to confront the theory with observations, one has to use the PPN formalism. And just, schematically, I show you here, for example, the Horndeski PPN parameters are given by these beta and gamma formulas. Of course, these are lengthy expressions of the arbitrary functions of the action, and details can be found in this paper as well. So just a take-home message. Horndeski gravity is the most general scalar tensor theory in 4 dimensions, leading to second-order field equations. However, it was severely constrained from the gravitational waves. TGR, the teleparallel equivalent of general relativity, is built in another geometry, meaning that it exploits torsion instead of curvature. And the combination of the two creates, of course, the teleparallel analog of Horndeski theories, which it does indeed include much more phenomenology than the standard Horndeski. Yeah, thanks a lot. Actually, this painting, Gregory Horndeski in the 70s, when he introduced his theory. After his PhD, he left physics and he became a painter. And when in the 2010s Horndeski theory was popular again, he started doing physics again. So this is a painting from Horndeski himself.
This talk is very much on time. Thank you all for time for questions.
Very interesting.
Thank you.
And you said that basically this framework is equivalent to a curved spacetime. In that case, what do you mean when you say that this framework fits better with Newtonian gravity?
Well, in the sense that Newtonian gravity could hold also without the equivalence principle. Okay. For example, here, as I said, this is a gauge theory of the translation group. So let's say it resembles more to U1. And you can see here, for example, that it acts like a force. So it's not geometry anymore. So if you take the gravitational mass and the inertial mass to be different, and you do the gauge transformations, you will end up, for example, with another factor here as well, which of course, if they are the same, it will vanish, but if they are not, it still could survive, let's say. So this theory does comply, let's say, with the equivalence principle, but if we are to, I mean, at some point we find some violations of the equivalence principle, this could survive while GR would not.
Okay, thank you.
Thank you for the interesting talk. I have just a question between the analogy of Horndeski and Teleparallel. So the only modification is just in the term of G4 and the additional terms coming from Teleparallel, and how you...
The only modification compared to what? I mean...
To Horndeski.
Okay, here, this is just Horndeski gravity translated into the teleparallel geometry.
So you keep
the yeah
minus t plus b.
Yeah.
Ah, okay, in the same time.
But we also have this extra function here because of the fact that the torsion tensor depends on first order derivatives of the tetrad.
But how you could know that the same Lagrangian will remain the same in teleparallel just by changing just R?
I don't understand.
Like the Horndeski Lagrangian,
yeah.
How you know that it's the same exactly?
Well, this is the Ricci scalar. So as I showed you before, the Ricci scalar is minus t plus a boundary term, and this is the Einstein term, the Einstein tensor written down in the teleparallel geometry. So it's just, let's say, a different. Yeah, it's just a different geometry.
Okay.
It's the exact same theory
for the scalar field for everything.
Yeah. I mean, it's a scalar field in the teleparallel geometry, and then you covariantize it.
Okay.
Exactly as I showed before in
how you explain the additional terms? Did you just guess what are the most general terms in teleparallel framework that can lead to second order equations?
If you start from the Galilean in flat Minkowski space, and you covariantize it in the teleparallel geometry, which is the torsional geometry, let's say, you will end up with this theory. Of course, you could construct it. These two theories, this Lagrangians and the Horndeski, are exactly the same. When you introduce this GTL, this could also have some extra terms, like, I don't know, quartic and quintic contractions of the torsion tensor. But one of the conditions that we used to construct this theory was to have up to quadratic orders.
And why you said it's physical in the quadratic order? What is the argument?
Yeah, maybe physical is not a correct word, but I mean, we had to stop somewhere in order to do some applications.
Yeah.
And you could include higher order in principle, but it's like having, for example, contractions of the Riemann quadratic. Yeah, not only quadratic, but also quartic and quintic contractions of the Riemann tensor in your theory. So,
okay.
Yeah, we had to formulate
like more computational argument.
Yeah.
Okay. Thank you very much.
Talk of the session is by Pfeifer on deformed relativistic kinematics on curves.
Yeah.
Okay. So, hello everyone, can you hear me? I updated my slides last minute. Hello, everyone. Thank you all. Okay. No, this doesn't work. Or is it the other? No. Okay, it works. Okay. Hello, everyone. Thank you all for coming. It's a pleasure to have a conference in person again. And during the school and also already today, we heard about deformed relativistic kinematics. That in the DSR framework and in the connection to quantum gravity and deformed special relativity, these models are much investigated and well motivated. And in my talk, I want to present ideas how to implement these deformed relativistic kinematics on a curved space-time. Let me just quickly recall why I think this is important. When we look at physical processes on curved space-time, like a gamma ray burst from an early universe, the curvature of space-time plays an important role. It tells us about the redshift, and other curvature effects may affect our observation. Another famous curved space-time effect is when you consider a black hole, a rotating black hole. Then you have around this black hole the so-called ergo region, and when you look at collisions of two particles in this ergo region, another particle, there can be a particle produced which escapes from the black hole ergo region, which extracts energy from the black hole. This is a genuine curved space-time effect, and in particular the energies, in the last recent years there have been papers who showed that the energies of these collisions can be very, very high. And sure, in flat space-time, when you just do a special relativistic calculation, this effect would not be present. So curved space-time effects are essential when we study the properties of gravity. And I think when we study the properties of quantum gravity, we must bring these ideas from deformed relativistic kinematics on flat space-time and the ideas of curved space-time geometries together. And here is a conjecture how one might do that. And this is joint work with Xavier Relancio and based on ideas of the group in Zaragoza. So quick outline of my talk. So I want to motivate this idea or show you this idea, how one can implement deformed relativistic kinematics on curved space-time. Then I want quickly introduce how we get a consistent geometry of how we can mathematically formulate a consistent description of curved space-times with curved momentum spaces. And then we'll do a perturbative analysis of some models to find constraints on deformed relativistic kinematics if we want to use certain geometric concepts and assumptions on the geometry to put them on curved space-time. So let's start. What are deformed relativistic kinematics? We already heard from Jose Manuel today in the morning the main ingredients. Let me repeat them. So they come with a modified law of addition of momenta. They include modified Lorentz transformations and the modified dispersion relations in general. Sometimes not all of these ingredients are present, but to have this deformed relativistic relativity principle, we need the modified addition of momentum consistent with the modified dispersion relation. So the modified addition of momentum changes particle interactions. The modified Lorentz transformations change relativistic observer effects like time dilations, length contractions, and everything, you can imagine, which comes from the observer effects in special relativity, while the modified dispersion relation changes on the one hand, gives you a modified energy conservation, which changes particle interactions, but also on a curved space-time, this changes the propagation of particles because we determine the curves on which particles propagate from the dispersion relation. So one famous model is the kappa Poincaré modified relativity in the bi-cross product basis. For this case, this F is given by this form. The modified addition law, we have modified Lorentz transformations, and we have a first order modified dispersion relation. Just to give you an example how this may look like. So now the idea that these deformed relativistic kinematics can be interpreted from the point of view of a geometry of the of momentum spaces is quite old, and there is a nice formulation of that by Jose Manuel and collaborators from last year, 2 years ago already. And the idea is the following: so we have a flat space-time and we have a curved momentum space, and we equip this momentum space with a momentum space metric. In particular, we can equip it with a maximally symmetric momentum space metric, and this metric has 10 isometries. It has, which are 4 translations and 4 rotations, and together 6 rotations and boosts, which are the Lorentz transformations. the translations in momentum space, sorry, so if you just move along here, they take a vector p and move it to another vector, and we can imagine that this goes along a curve here, which is parametrized by yet another momentum here, or described by in the direction of another momentum here. The rotations and boost, they take a momentum, and yeah, boost it and rotate it to another momentum. And infinitesimally, as done on curved spacetimes, you can generate these boosts and rotations, as well as the translations, infinitesimal by vector fields on this momentum space. And technically, the momentum space on a flat spacetime, I interpret them mathematically as cotangent spaces. Then the translations, the generators of translations, or these translation maps, the translation isometries define the addition of momenta. The boosts and rotations define my modified Lorentz transformations, and the dispersion relation is given by the square of the geometric length in momentum space defined by the metric length measure here. And so the minimum length, so you look at the geodesics in this curved momentum space. Yeah, now let me show you an example of a maximally symmetric on such a curved momentum space. We could simply just take this representation. When you look in books about maximally symmetric metrics, this is one representation in quasi-Cartesian coordinates, which is built from a metric, so from a independent metric, and some momenta here, which are just the coordinates on the momentum space. Now the question is there a procedure to lift this on a curved spacetime? So we want not to consider a flat manifold, but a curved spacetime manifold, which we equip with a spacetime metric. And the conjecture is the following: that we simply replace these flat metrics here by the curved spacetime metric, or alternatively, we rotate the momenta with the frames of the metric, and then obtain this the curved spacetime version of this maximally symmetric momentum space metric. So at each point of the curved manifold, in the way that we simply rotate this momentum space metric into the new frame and replace the momenta by these rotated momenta. And then the expression looks like this. So we have a position-dependent momentum space metric, which is maximally symmetric at each point, constructed from a space-time metric and the momenta. What happens then is that these generators of translation and the generators of boosts and rotations become position-dependent, or these isometries become position-dependent. But at each point of space-time, now you have a well-defined or geometrically defined modified addition of momentum given by these local generators of translation in momentum space. You have boost and rotations given by the local infinitesimal given by the local generators of rotations and boost, and you these are isometry in momentum space, but at each point of the manifold, so they are point dependent. Both. They depend on x and p. So yeah, you have basically they are constructed from this momentum space, from this space-time dependent metric. So imagine you fix the x here, then you have basically you use this x just for the moment as parameter. Then for each x, you have your generators of rotation and translation in momentum space. But they're different at each space-time point because your metric here, this A, is different at each space-time point. In momentum space. Yes. No, they're your translations in momentum space, and they are interpreted as generating this law of addition of momentum. This idea was taken from the paper by José Luis Cortés and Javier Relativistic, and we simply now added this curved spacetime idea to that. Yeah, and also what you get that the dispersion relation you take as minimal length in each of these momentum spaces, so you can simply think of having a copy of this at each point. Yeah. You have a copy of your tangent spaces of cotangent spaces of each point, but at each cotangent space you have a different space-time metric. It's like you have the different scalar product in each cotangent space that gives you curvature, And now it gives you a different momentum space metric at each space-time point. Anyhow, everywhere it's maximally symmetric, at least when you use this simple example here. There are more. In the sense of the momentum space, I mean, you have these 10 isometries in momentums, in each momentum space. At each space-time point, I have them in the paper. I don't want to write them down here. No. These are the isometries at each point. So you define you could define an object maybe like this. Maybe this makes it more clear. So you define a momentum space metric. Let's call it again zeta AB, which a label x, which just depends on p, which is just GAB of xp. So, and these objects here, where you use x just as a label, you have the rotations and translations in momentum space for these objects. But they are different at each space-time point. This is exactly the point. Okay. Now I talked a lot about these maximally symmetric momentum space metrics, position-dependent momentum space metrics, and there are some caveats here. Yes, we can change the momentum space basis here, and this would give you different presentation of these deformed symmetry, deformed relativistic kinematics. And also you can change the definition of these translations here according to this linear combination. So you mix translations and the boosts in a certain way. This gives you different representations of different models of deformed relativistic kinematics. But in principle, when you have set it up in one system, you can generate all others. Okay. Now, this should motivate why we want to look at position-dependent momentum space metrics, so metrics which depend on x and p. So let us study geometry of such metrics. And the position-dependent momentum space geometry. And technically, this is, we look at curved spacetimes and curved momentum spaces. And technically, we could, physically would call these curved phase spaces, point particle phase spaces. And mathematically, these are the cotangent bundles of a spacetime. We equip it with some coordinates. So if you take an element of this cotangent space, that's a one form on spacetime, which has some components. When we take some coordinates on the spacetime and we simply label points in this curved phase space by x and p, where x is really just a point on the base manifold and p are the components of a momentum with respect to a coordinate basis. So to do geometry, we must look at the tangent spaces. If this, basically, you can look at this picture. There are a lot of formulas coming now. To study geometry, we must look at the tangent spaces of the manifold of the cotangent bundle, and we have a tangent space to momentum space, this blue one here, which is just generated by these d by dp's, and you have a complement to that, which is generated by the d by dx coordinate vector fields. But then we can ask the question if this really is a tangent space to space-time, if we can interpret it like this, and this is a complication here in this approach, that this cannot be interpreted as a tangent space to space-time, since if you do a coordinate transformation of space-time, these partial d by dx and d by dp's, they mix. So this split is not preserved. So you cannot really identify these simple tangent spaces as the ones which describe the tangent spaces to a curved space-time coordinate invariant. Therefore, one has to introduce a so-called nonlinear connection and introduce these delta derivative operators, which tell you how you have to, so to say, curve or relate the tangent space to space-time, or put the tangent space to space-time into the tangent space of the cotangent bundle. It's very technical, but this ensures coordinate invariance. That this construction is invariant under coordinates transformations on the base manifold, because this is definitely what we want. Okay. When you look at usual space-time geometry, just with a connection or with the only position-dependent metric, then you would this what is called nonlinear connection is an object which is linear in the momenta, given by some affine connection coefficients, and that's also why in general this object is called nonlinear connection, because it's nonlinear in the momenta. We'll see an example later. And then there are important curves here. On the one hand, we have curves which just move in the momentum space. These we need to define these deformed relativistic kinematics. These are called vertical trajectories. And we have curves on the manifold, which shall be our point particle trajectories, physical point particle trajectories. These are so-called horizontal curves, and they have to satisfy this equation here, which involves this nonlinear connection. On the basis of general relativity, this would be the geodesic equation of a metric, or of this connection you use here. And now we can introduce a metric completely on phase space generated by our momentum space metric. So this is a complete metric on the whole curved phase space. And this we can use to do further geometry and identify the geodesics of this metric. So we have, on the one hand, we have the ones which we interpret as particle trajectories, and we have the ones which give us the distance in momentum space, which are exactly the geodesics of this length measure we saw earlier. And these objects H and C here, they are built like the usual Christoffel symbols from this metric components here, where for the H you use the delta derivative, so this partial should just be a placeholder for derivatives. And for the vertical ones, so the curves in momentum space, you use momentum derivatives. Okay, this is how you construct such a geometry, just to remind this, because we want to give these trajectories physical interpretation. And now I want to mention two principles which we want to implement on this geometry. On the one hand, what we heard earlier, so the dispersion relation of physical point particles is defined by the minimal geometric distance in momentum space. And the second one is that the solutions of the Hamilton equations of motion determined by the dispersion relation are horizontal curves, so that they are adapted to the geometry, and thus can be interpreted as force-free, freely falling particles only subject to gravity. And the first one is we use this definition of the length of the this should be p's, sorry. Okay, we use this definition of the metric length, and now we are looking at we want to have the minimal distance. The minimal distance is characterized by the geodesics of this length measure, and we just want the length in momentum space. Yeah, this can be calculated. So you need to solve these two equations here, and you have a curve in momentum space which is which connects the origin of the momentum space to some arbitrary momentum which you are interested in. And then there is a mathematical theorem that you can obtain this dispersion relation object here, so the Casimir or Hamilton function of the system, via this partial differential equation, which connects the space-time position-dependent momentum space metric with this length measure. So the second one is that the Hamilton equations of motion, let's look at this second Hamilton equations of motion, which usually is the geodesic equation in general relativity, determined by this dispersion relation on curved spacetime, can be written in this form by introducing this nonlinear connection. And now if we want that this really is a horizontal geodesic, horizontal curve, so a pure spacetime curve, so to say, we can compare it with this expression, and we see that we need to conclude that we want a geometry where this dispersion relation or Hamilton function is constant along the manifold directions. And then combining this and this equation, we get a third constraint which relates the nonlinear connection with these geodesic equation coefficients. So what we find is, if we want to establish these two concepts on a curved spacetime with curved momentum spaces, the geometry must satisfy these three constraints, mathematical constraints, which intertwine the metric and the dispersion relation, the nonlinear connection and the dispersion relation, and these horizontal curves and geodesics. So, which momentum space metrics satisfy this constraint was the question we asked next. And therefore, we did the perturbative analysis. So we looked at the momentum space, position-dependent momentum space metric, which is has a zeros order, which is not momentum dependent, and then some polynomial perturbation. In a moment, we will set n to 1. And this epsilon is just your perturbation parameter. In the context of quantum gravity, it would be 1 over this Planck Planck energy or something like that. For the dispersion relation, again, we do a perturbative ansatz. And for this nonlinear connection, also that we have in zeros order, we just have the usual connection from general relativity plus some correction. Now, let's look at the constraints. By the way, how am I in time? Okay. So let's look at the first constraint. You can solve it perturbatively, and what you find is, so this intertwines the metric and the dispersion relation. We assumed them to be independent a priori. So you find that this coefficient here and this coefficient are identical, and this perturbation here and this perturbation, that they are basically proportional to each other, where the the power of the polynomial perturbation in the momenta plays a role here. The second constraint tells us about the dispersion relation and the nonlinear connection, how they are related. And there you find a relation between this x and this b, but this b was already expressed by the small b. So in the end, you find a relation between the dispersion relation and the momentum space metrics. And what you find is this covariant derivative in the perturbative approach is just the Levi-Civita covariant derivative of this metric. So you find that the corrections, the momentum-dependent corrections to the connection are generated by the covariant derivative of this of the perturbations of the metric. And for example, you could construct a geometry which is really just GR by demanding that this is covariantly constant. And then the third constraint, which is the most restrictive one, connects the geodesics and the nonlinear connection, where I didn't tell you what, no, I told you what the H is. So these Christoffel symbol objects with this nonlinear connections, and this yields to this equation. You see that here again we have the covariant derivatives of the perturbation of the metric. And when you look at the symmetries of these perturbation of the x and the b, you see that the oh, I think here is a mistake. Okay, we will see it in a moment. That you here need a symmetrization between C to Cn, and here you see you only have a symmetrization to C1 to Cn. So there must, the right-hand side, in order to be consistent, must satisfy that somehow, when you calculate these expressions here for a specific model, that the symmetry appears between the this C and all the other C's here. We will see this in a second. So, to make this a bit more clear, what's happening here, let us look at the n equal 1 perturbation. So the metric gets a term linear in the momenta and the dispersion relation cubic in the momenta. And this is what is studied very often in the literature. Yeah? This you see for deformed special relativity a lot. And then we find from the previous slides that here we just get, here this x is related to the, oh, there's a mistake, I'm sorry. This cannot both be x, or? Oh, what did I do? So these equations are contradictory. I did this mistake somewhere. Anyway, I'm sorry. So I think this shouldn't be x. But this equation is the important one. So since we have here this symmetry between C1 and C, but on the right-hand side, the symmetry is not necessarily reflected. Forget about this equation for a moment. I'm really sorry. Yeah. So let us look at explicit examples. So now this is a constraint on the perturbations which I can implement here. Yeah? And we can, for example, look at the perturbation which is generated by a space-time metric and the derivative of a scalar field. Then the dispersion relation takes this expression. I just plug this b in all of these equations, and I find that the this perturbation of the connection takes this form. Due to, since the metric is covariant constant, all these covariant derivatives become very trivial, and these terms sum up. And you see that this here's no problem with the index symmetry. So this is symmetric in A and B and C and D. And if you want to expand this in a more hands-on form, this dispersion relation would be of this type. So you have the usual Lorentz invariant dispersion relation where I chose the signature convention minus plus 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 here, and you get a correction which depends on the derivatives of this scalar field. So corrections are really connected here to the scalar field, and there's no inconsistency in the geometry. So really get what we really get a consistent geometry from such a perturbation. Yeah. Now let us look at kappa Poincaré. There, the correction to the momentum space metric is given by this form. You have a term which goes with the metric, and a term which goes with a vector field. This is just a time-like vector field on space-time, usually interpreted as the direction of the energy. You get the deformed dispersion relation, where you here have the spatial, the norm of the spatial components of the momentum, and here the energy, and you get this expression for the correction to the connection. Yes, and so you can expand. So this term you can in a frame expand like this, and here you see more directly the relation to the usual how the Kappa-Poincare dispersion relation is usually discussed. So, but here's a problem, because on the left-hand side we need this x to be symmetric. On the right-hand side, this term is symmetric in C and D, but this term not, and these terms also not. Yes. And the only way, when you study this a bit, at least this was our conclusion, is that the covariant derivative of this vector field must be 0 to satisfy this equation. So you have a 0 on the right-hand side, and then this object is certainly symmetric. However, covariant constant vector fields do not exist on all curved spacetimes. So if we really want this, then we couldn't lift the Kappa-Poincare dispersion relation to all curved spacetimes. And the conclusion is, if you really want this force axioms to be satisfied, so that the distance of momentum space gives you the dispersion relation, that the Hamilton equations give you the geodesics of the geometry, that a lift to generic spacetimes exists. So not that you can only lift a certain modification here of the moment, a certain momentum space metric to a certain curved spacetime, and then you can consider these models where there is a vector field appearing in the momentum space metric as for Kappa-Poincare. And then the implication is that this perturbation actually is not allowed to depend on such a vector field. That means that you need to find a representation of your deformed relativistic kinematics in curved momentum space, where the momentum space metric only depends basically on a metric. Okay, and this is already it. Let me come to my conclusions. So we started from 4 assumptions. Namely, I started with a geometry of curved spacetimes with curved momentum spaces, where this separation between momentum space and spacetime is coordinate invariant. I think this is the first step we may all agree on. And then the distance in momentum space is interpreted as the dispersion relation, which leads to this constraint. And then that the Hamilton equations of motion give you the geodesics of the geometry, which leads to these 2 constraints. And then we said that the lift of the momentum space metric from a flat momentum space metric on flat spacetime to a momentum space metric on curved spacetime, that should exist and work like this, that we replace the momenta with these rotated ones, and that we then generate from the flat spacetime momentum space metric the curved spacetime momentum space metric. Then the conclusion is that if there is a vector field in the flat, if there is a preferred vector field in the flat momentum space metric, which you need to construct this does not lead to a consistent curved spacetime geometry satisfying these assumptions. Then we saw that there exist non-trivial curved momentum space metrics on curved spacetime, which are generated by a metric and a scalar field, which satisfy these 3 assumptions. However, they cannot not so easily be connected to a flat spacetime curved momentum space metric via this procedure. And if you have your modified deformed relativistic kinematics and you find a momentum space metric such that your momentum space metric only depends on the Minkowski metric on flat spacetime, then you can lift it satisfying these 4 axioms. So, and the example I showed you in the beginning is such an example. This works perfectly fine. Then, what you find is, then there's something a bit more boring happens, that you find is when you have such a momentum space metric, and this holds in general, which just depends on the spacetime metric, then the dispersion relation is just a function of this Lorentz invariant object. Yeah? So you have no modified dispersion relation effects in such deformed relativistic kinematics, but only effects from the addition of momenta. And this now can be seen as a positive selection criteria in the sense that, okay, we avoid all the constraints in these models which come from propagation effects, time delays, and so on, and only get constraints from the threshold effects, from the interaction of the multi-particle system. Yeah, so no single particle effects. Or you say, okay, this may be boring because I exclude so many models here. Then I can say, okay, to evade this conclusion, I can remove some assumptions. And I think one assumption one could, for example, remove is that you identify the Hamilton equations of motion with the horizontal geodesics. Then your Hamilton equations would have a source term, But I don't see any problem with that. It would be a bit, yeah. Then you would simply have like a quantum gravity force or something acting on your particles. Okay, thank you for your attention. I'm here for questions, and yeah.
So my question is maybe naive, but I didn't really understand the initial point of this formulation, because you basically start with a space-time, say with a space-time, and then you attach a fiber to each point, getting a fiber bundle. But so basically, physically, if in the framework of DSR, basically, I can say that a point is a point only locally, because if I see distant observer, I don't see something which is local does not become local for distant observer. So what happens? Do I have n fibers for distant observers, or are you just attaching one fiber to each space-time point locally? But then, if this is the case, if you're rotating geodesics which are not surface forming, then I don't see how this applies to general metrics in space-time. So I don't know if it makes sense.
I don't know if I understand your question completely.
So basically,
you're right. I mean, we're looking just at the we're looking at the cotangent bundle as a fiber bundle. So at each point of space-time, you have one momentum space.
Yes, this is what I'm trying to understand, because so in double spatial relativity, basically let's define an event like as interaction, like we saw yesterday. So if I now move 200 kilometers, I will not see this space-time point, which was defined by this interaction, as a space-time point anymore, because there is relative locality. So yeah, so the question is basically how does this attaching a fiber to each space-time point connects with this?
That is a very good question, and that is something we should really find out, because it depends from which viewpoint you start. I come from a general relativistic point of view, and what you do is exactly when you go from flat to curved space-time, you localize your symmetry group. Yeah, so you really, that's what you do. You have your Lorentz symmetry. First of all, you don't have translation symmetry anymore, and then you localize the Lorentz group to each tangent space or cotangent space. Yeah, this is what happens in general relativity when you go to curved. From flat to curved space-time. And now what I have in mind is to interpret this as, now you have general relativity and do these deformations in each space-time point, in each cotangent space. So you go from Lorentz transformations to deformed Lorentz transformations at each space-time point. That's at least the picture I have in mind. How to connect this with the fact that when you start with flat space-time, with the DSR, and that you get these relative locality effects, that's still an open question how they appear here, yeah? Because a lot of these effects appear due to that you use, we have it here, that you use translation operators here, yeah? But on a curved space-time, translation operator, you don't have translation symmetry. You only don't have Poincare symmetry, you just have local Lorentz symmetry. So this is something I think one should calculate from both sides and see where we meet, because that's something I don't understand how this works, yeah? Because this you can only do if your space-time is maximally symmetric. But I mean, we know we have black holes, we have curved, we have rotating black holes, so you need to do some calculations in curved space-time, and in curved space-time you don't have translations. I cannot use a translation operator. What I need to do usually is to do some parallel transport to compare events at different points, or to say what a distant observer sees at a certain event. I need either to propagate all my physical information via geodesics, or I need to get the information by a photon which reaches me, yeah? So, and then if I reconstruct where this photon emerges, maybe that is what happens. So you have an event, collision of particles, and then some photons emerge from that point, and they propagate on some world lines, and some observer observes these photons. And then maybe when you reconstruct it, that the distant observer, if it's moving relative to this source, cannot reconstruct one single vertex, but finds that these world lines didn't meet or something. Maybe something like this happens. Yeah.
Okay, thank you.
But this is certainly not worked out.
Hello. I wanted to ask you this assumption that you impose on this restriction on the possible metrics of space. what is do they have a physical meaning or just?
I mean, the first one is this this idea that the distance and momentum space gives you the dispersion relations. Yeah, this appears in the context of relative locality. And this one is exactly the question of this force-free motion. Usually you say you have a pure geometric motion, and then you can interpret your particles as freely falling, really not feeling any force. If you have a source term, so this would be the right-hand side of your geodesic, so you have the geodesic equation equal some source term, then you can, so to say, not locally gauge it away. So then you would say, okay, my particles are not freely falling in the geometry, but they feel some force. So this has to be made more precise, I agree, but this is simply when you look at the equation, this is what you would naively, how you would naively interpret this. And now the question is, do we insist in these DSR frameworks on this basis, on curved space-time, that to interpret the Hamilton equations of motion as force-free motion, or do we need to modify them? And here I speak of the Hamilton equations of motion only given by the dispersion relation. This is what I found very interesting on Jurek's lecture on DSR. There he modified, due to the modification of the kinetic term, these resulting particle equations you get, they're not longer here, they are not purely the Hamilton equations of motion by the dispersion relation, but get a non-trivial contribution from this kinetic term. And this is then also something different. Yeah, but this is something. So here I really assumed that the motion is completely determined by the dispersion relation, which is on curved spacetime just the Hamilton function of the point particles.
Yeah, hello. So this is something that I probably missed at in the beginning. So you showed that metric on momentum space. You showed that you said that the momentum space had to be maximally symmetric.
Yeah.
But then when you take the metric eta and you substitute it with a generic spacetime metric A, since it depends on the point, how are you sure that when you fix a point, you still get a maximally symmetric space for momentum space? Is it just in the definition, or
no? You can calculate it. I mean, the definition of a maximally symmetric space, just any manifold, yeah, is that you have a constant curvature, and this is this k, and you can simply calculate it. You see it. Okay, you fix the x and just, I mean, you just take p derivatives. So you look at this metric here, you forget about the x dependent. The x is, you put some value, 7, 8, whatever point you like. So some point on the manifold, and then you just look at this as a function of p, as a metric on some manifold which depends on the p coordinates. Then you calculate the usual curvature and everything, and you see it's constant.
Okay, great.
And this is in short. This is exactly in short by this procedure here. That you do this lift, and you do the same for the generators for the isometries, and you simplify that these at each space-time point these are still isometries. Okay, that's implemented in the construction. But it doesn't say anything about the symmetry properties of the space-time. Yeah, it's only symmetry properties of the momentum space at each point, and I think this is very nice because it's something from my point of view independent. Yeah, you can look at a spherically symmetric space-time with maximally symmetric momentum spaces.
When you calculate the curvature with this other metric by fixing x, you always get constant.
Yeah, okay, exactly.
Perfect. Okay, thank you.
So the comment is that you all received an email with details for the welcome reception this evening at the theater. But I remind you that it is necessary to present COVID vaccination